In this video, we're going to talk about how Lambda handles cold starts when it gets more requests than it has capacity for. A lot of us think that there's a queue, but there's not. Let's look at the results that we're going to see demonstrated in a moment. When we send one concurrent request and there's no initialized execution environments, we're going to see one cold start time. This is with an application that simulates a 7-second cold start time with a sleep in the global scope with an async await. We're going to see one request gets delayed by a cold start. We're going to see in the logs there's 3 starts happening. There is some pre-initialization in Lambda that does end up helping us. We're going to get roughly 3 total exec environments in that case. When we send 10 concurrent requests just after that, we get 8 cold start times. We see an additional 16 inits in the logs, giving us roughly capacity for 19. When we then send 20, we get no cold start delays. We see more inits in the logs. Keep in mind, these aren't going to be at exactly the same time, so some of these inits actually happened before we sent 20. We had a total capacity of about 35 after this was done. When we then send 100 in parallel, we get 76 additional cold start delayed responses that take 7 to 8 seconds. We see another 217 in the logs of inits. So there's roughly 252 total execution environments at some point between these two. So when we send 200, we get none because we've got roughly enough capacity. When we then hit it with 400, we see 168 second response times, more initializations, and roughly 458 total capacity. You see the pre-init is staying a little bit ahead, but it's not usually able to handle a doubling of request load. There are other circumstances under which this can be a problem. If you use, for example, the latest version of your Lambda and you don't use an alias with versions and traffic shifting between the versions slowly over the course of many minutes, then if you change anything on the Lambda, if you change the memory request by a meg, an environment variable, you will cause all of the execution environments to be destroyed simultaneously. And you will then immediately go back to this case. And if you're running at a concurrency level of, say, 400 or 1,000, you're going to have tens of thousands of instances of your Lambda try to start at the same time. Because if, for example, you have an 8-second cold start time and a nominal response time of 0.1 seconds, every 0.1 seconds that goes by needs to start an additional number of that many instances in order to handle the additional incoming requests that you're getting. This is how we wish Lambda worked in this case. We wish that if we got 6 requests, that 3 of them at time 0 would immediately be dispatched to 3 execution environments. Additional execution environments would start spinning up because it sees that we're going to need extra capacity, but they're not going to be available for 8 seconds in our case. The nominal response time being 0.1 seconds at T1, which is 0.1 seconds later in this case, request 4 gets dispatched to execution environment 1, 5 to 2, 6 to 3. And when additional requests come in, the same thing happens. And eventually when these additional execution environments are available, the queuing delay becomes shorter. That's how we wish it happened. Unfortunately, this is actually how you can observe that it works and how we'll demonstrate that it works in this video, which is if you get 3 requests at time 0, they go directly into those execution environments. There is no queue. The second 3 requests, also at time 0, no delay here, immediately cause an additional 3 execution environments to start, assuming there were none pre-initted already. And these requests are bound to these cold starting instances. Even though these execution environments will be available 0.1 seconds later, these requests will wait the entire 8 seconds for these execution environments to completely finish their initialization. This happens, I think, because there is no queue. They don't want to have a shared resource that could get full of requests and be another thing they have to tell us about the capacity constraints for it and costs and so forth. So what they do is they just say, this request came in, we don't have an execution environment, let's start one and let's send the request to that execution environment and have it just sit there until that instance either succeeds or fails to init and the request runs. That's what we're going to demonstrate in a moment. So sit tight and don't forget to like and subscribe. It really helps. Thanks. Let's do a demo of Lambda scale-up for web requests. Many devs believe there's a queue. When too many requests come in and there's not enough Lambda instances, that the request will be queued and dispatched to Lambda instances as they become available. However, that is not observably true. What we will see is that if too many requests come in, they will force the cold start of a new Lambda instance, and we will wait the entire duration for that instance to init. There is a small percentage of preemptive cold starts happening now. AWS has been making changes around this in the last year. So if we send in 10 requests in parallel, we may see that there are 13 initialized instances. If we send 100, we may see there's 130 initialized instances. But if we send in a burst of requests, we will generally see that many of those are going to have to wait for a new instance to cold start. Let's look at our test application. It's a Node application over here, written in Node.js. It's got 128 megs of RAM. I fiddle the amount of memory by a megabyte to get it to discard all of the execution environments. That's a technique you can use if you want to reproduce this test. What we'll do now that there's no execution environments is we will run one ping request. And this application has a 7-second cold start. It's simulated. It's a ESM application, just called sleep at the global level. And the Lambda runtime will wait for those global async awaits to finish. We can see one instance started, took about 7 seconds. If we run it again, it's going to come back right away. Now, if we run OHA with one concurrent request for 10 seconds, actually let's go with 15, and we do so what's odd is that after the first request is sent, it seems to stick the next request to another initializing instance. I'm not quite sure why, but that's an unpleasant experience. So you can see here, one request waited 8 seconds for that cold start. Now if we bump that up to 10 concurrent requests, we're doing this from a Cloud Shell so that we minimize the round trip time and can actually send approximately the number of concurrent requests that we're asking for and have them arrive at the Lambdas at the same time. So what we'll see here is it's going to go at 100 RPS, and then right when it gets to 8 seconds, it's going to jump. And the reason for that is that the requests that were stuck behind a cold init were finally able to get through. So 8 of our 10 sockets were stuck waiting for an 8-second initialization. Meanwhile, the other 2 sockets were able to handle some requests in the beginning, getting about 100 RPS. And then as the other 8 sockets were unblocked, we got substantially higher throughput. And if we run that again, we'll see that we get that higher throughput from the beginning. Okay, that's enough of that. Let's jump it up again. Let's jump to 20 parallel. We're going to do HTTP2 here to minimize the number of open file descriptors. We're going to have 2 requests in parallel per 10 sockets, so we're going to get 20 total. We should see an additional burst or increase in traffic rate when we get about 8 seconds in. Maybe we won't. We might have gotten enough pre-initialized instances. Yeah, we didn't see any delay this time. So let's give it a little bit of a tougher problem to solve here. Let's give it 100 in parallel. Yep, there's the burst. And then let's see how many waited. 76. So out of 100 parallel requests, 76 waited for a new cold starting instance. And if you think about that, the other 24 instances that were available, they finished one of these ping responses a few milliseconds after these requests were received. But these requests were, as I call it, glued to a cold starting instance. Let's bump this up a little further to 200 in parallel. We should see, again, maybe another 76 that are waiting for a cold starting instance. Oh, we got none that time. Let's try going to 400. Now we're starting to see a problem, which is odd with Lambda. It happens when your response time is less than 100 milliseconds. The total account concurrency limit of 1,000 in this case actually stops you from doing more than 10 executions or invocations of a Lambda per second for each of the 1,000 concurrent Lambdas that you're allowed. So that's going to limit you to about 10,000 requests per second when you have that set to 1,000. In this case, when we breach that, we start getting 502s. But in any case, 160 of the additional 200 requests that we sent in parallel waited for a new Lambda to cold start. You can see there's not really a queue. Occasionally we get pretty lucky and Lambda has pre-scaled and has additional execution environments available for us, but if they don't do us any favors. We wait for a cold starting instance, and if your application has a long cold start time relative to the average response time, it can cause a very large number of Lambdas to start up and then immediately not be needed. We can see in our dashboard, we got 8 cold starts, then we got an additional 77 cold starts, and that was a few minutes ago. We should see those other 130 or so cold start response times come in here. This is tracking the trimmed count from the perspective of the load balancer, anything with a response time greater than 6 seconds and less than 12 seconds. So it should show that full 160. Hey, there we go. There's that extra data point we were looking for. So it came in. So it's not just that Cloud Shell, for example, didn't have enough CPU and wasn't able to get a response in time. It's that the response from the ALB actually was held up for that full 8 seconds. Here is some additional data about the cold starts. Here we can see the load balancer's perspective of the cold starts. We can see the corresponding request count going through the ALB. So here we're looking at whether or not a request had a response time over 6 seconds, whether or not it got a cold in it. We see there were 2 in the beginning, then there were 8, then there were 0, then there were 77, then there was 160. If we come down to the actual tracking in the logs of when an init duration was printed, we can see that we start with, during the same lined up time here, 3 inits, then 16 inits, then 16 inits, then 217 inits, and then 206 inits. That is why we got 2 instances where we did not have any cold start delays, because the 16 inits and the 16 inits gave us around a capacity of about 35 when we sent it 20 in parallel. So it had enough instances pre-initialized. And when we went from 100 to 200, we had approximately a total of 252 instances that were initialized, so there was enough capacity to handle that. But when we went from 20 to 100, we did not have enough capacity, and when we went from 200 to 400, we did not have enough capacity. That's why we saw the cold start delays at that time. So if pre-init has enough capacity for you and your burst is within that, you're going to be fine. But if you go over the amount that's initialized, all of those concurrent requests will start a new execution environment, and they will all wait, or they'll get throttled and rejected. Not just for the reason we saw with the response time less than 100 milliseconds, but for actual throttling of just not being able to start enough instances.